Hello, I'm Rui, and today I'll be talking about the future of content delivery for the mobile app industry, and in particular the challenges that the wireless last mile presents to mobile apps. A little bit about myself. So I'm CEO and co-founder at Codavel, and today I will be sharing a little bit about what I've learned throughout more than 15 years working on wireless content delivery, in particular in network protocols. So today I will start by talking a little bit on why should we care about performance, why should we care about speed for a mobile application. Then I will give you just a little bit of insight on how should we look at performance, and then I will focus the remainder of my presentation on why is the wireless links today killing the user experience, and what are the roles that transport protocols can play in this equation. So, but starting from the beginning, so why does speed matter? It's common sense, but we actually get tons of market data that shows that faster apps get better business outcomes, being higher user engagement, higher conversion rates, more time spent in app, more ads shown to the end user. So in the end, faster apps typically mean a better business outcome for whoever owns the application. So, but when you look at this from the user perspective, so it's actually, in this graphic here in the bottom kind of strikes me, like when you list what are the priorities from the end user perspective, number one priority for the end user is speed, right? And when you look at what users feel about speed in a mobile application, 76% of them consider speed to be very or critical important. And if we include those that rated important in this question, we go up to 96%. So users care a lot about speed. But the question is, all right, so users care about speed, but does this reflect into something that is tangible from the business perspective? So I'll start by bringing you these two graphics from Farfetch. On the left side, you can see the plot of the conversion rate versus time to interactivity distribution. And so what you can immediately see there is that as soon as the time to interactivity of the application starts increasing more than 3 seconds, the conversion rate dramatically drops for all the rest of the graphics. So this basically means that if the app is slower than 3 seconds to provide interactivity, for Farfetch specific case, conversion rate dramatically decreases, which in the end for Farfetch means less revenue, right? More interesting is when you look at this graphic is the fact that if you look at the distribution of time to interactivity, you can see that the gross of the distribution is not where we wanted it to be. So in the region where the conversion rate were maximal, and this basically means there are a lot of user sessions that get time to interactivity that is just too high, and so user won't convert. This also has an impact, time to interactivity, also has an impact on the number of pages that people go through when visiting Farfetch. As you can see there, as soon as time to interactivity starts increasing, the percentage of user sessions that go beyond 3 pages starts decreasing dramatically. So a few other examples, like this one on the left is a well-known study by Akamai that shows that if you want to provide a video to an end user on a mobile application, you have 2 seconds to do that, and each additional second you add in terms of delay, you will be losing 5.8% of the users per each additional second. Right, so this shows clearly that if your video takes too long, people will just drop out. If we are talking about the social network, for example, that may mean leaving out the app or not watching the ad, so losing user engagement. And on the right side, it's also an interesting result by LinkedIn, which shows that the speed correlates dramatically in the number of sessions and the number of unique members or unique users that visit LinkedIn mobile application. And that impact is quite astonishing, in particular for those users who have slow connectivity. So to wrap it up, a few other numbers on why speed matters. We have the classical from Amazon, where they artificially added 1 second of latency to their site, and they basically concluded that each second they add in terms of delay, they will lose $1.6 billion in terms of revenue. But I would like to highlight this one from Snapchat, because if you remember what I've just mentioned about Akamai, where I said, or Akamai says, that you have 2 seconds to deliver a video and then people start dropping out. Actually, for the user base of Snapchat, it's exactly the opposite. If you take more than 2 seconds to deliver a snap, everyone moves on. So that basically means that you have up to 2 seconds to deliver a video to in the Snapchat application. And the reason why this behavior is changing, I guess, is due to the age, or the typical age of the user base of Snapchat being way much younger and less patient towards waiting for content to appear in their mobile apps. So, sorry. Diving into how should we look at performance. So people in some cases are used to look at performance or speed by looking at the speed of network calls or requests to the network. But for an end user perspective, he actually doesn't care about an individual HTTP call. What he actually cares about is an action. So for example, this is a typical waterfall for a social networking application. And so as you can see, like time to interactivity typically means 7 requests. So if you look at just one of those requests and think that everything is okay because that request is good, you may be dramatically wrong, because out of those 7, you only need one of those requests to go wrong to screw up the experience for the end user. And that's all the user cares about. And this obviously gets more dramatic when you try to look at time to first meaningful paint in the application, which in this case amounts to 16 different network calls. And when you look at what happens when the user is trying to interact with a post on this social network, this amounts to 25 different requests to the network. And so again, if you focus on one single request and that request is good, that does not mean that there is not another request that is screwing up the user experience. And so one of the places that typically the devil hides is in the tail. So what do I mean by tail in this case? So percentile 90, P99, P95, everyone has a different percentile they all like to look at. And so typical values for P90 and P99, for example, to fetch an image, we are talking about a median time of 240 milliseconds. And when you look to P99, we are talking about something that goes above 2 seconds to download a single image in the mobile application. And similar stuff happens for video startup time or rebuffering time. So meaning that obviously that P99 is, or P95 or P90 are way higher than the mean. And typically one thinks that, all right, but my average behavior is very good. So what's the problem if I have a very high P99, meaning that those 1% will have a bad experience, but the remainder will be okay. And this is actually wrong, because as the title of the slide says, rare is actually way common. So for example, for Snapchat, they concluded by analyzing user sessions that more than half of their users get a P99 experience at least once a week. So that means that more of the half of the users of Snapchat, so a leading edge mobile application, basically get a very bad experience at least once during a week. And when you look at, I love this table because if you look for the simplest example of all, which is when you look at the page google.com, so that white, plain simple page, so that page involves 31 HTTP calls, network calls, sorry, which basically means if you compute some, if you do some probabilistic computation, that the probability when you open that page that you get the P99 experience is 26.7%, which is 1/4. So again, you have to look at the tail for these statistical reasons, but if you want a more subjective reason, I love this quote that basically says that what users remind about your application is that when it fails, not when it works well. So, and the other reality today is that the mobile app industry is investing a lot in optimizing the mobile application to ensure a perfect user experience. But then in the end, what you see in the user's end is something that is way different than what mobile app developers expect. Sorry. So for example, today, more than half of the video sessions still get a buffering event. And a single buffering event, by the way, is sufficient to have more than 30% of the users dropping out of that video session. And so the experience is not only bad, generically speaking, but also it's highly unstable. So from one point you can have a very good experience, and then 5 minutes later your app is providing a shitty experience to the same end user over the same network on the same device, right? So for example, today, and this is again looking at Snapchat data, today more than half or almost half of the users have to wait for more than 11 seconds to start a video at least once a week. So that's quite powerful. And one may think that this problem is a problem related to network infrastructure, and so that it should happen more often in developing countries. But actually, if you look at Uber was one of the first that released this performance data globally. And when you look at what Uber is seeing in terms of performance, you can see that yes, so the reddish, the worse. So yes, in India, South America, in Africa, the situation is a little bit more dramatic. But still, even in Europe and the US, you have significant problems with respect to what our users experience with mobile applications. And going to this part of the main part of my talk, so what I'm going to try to convey to you is that the last mile, the wireless last mile, 4G, 3G, Wi-Fi, or even the upcoming 5G are the reason why today we still have so many problems with respect to user experience in mobile applications. So first of all, wireless is a completely different communication medium when compared to wired. So for example, if we are talking about a fiber connection, we have a packet loss, typically a packet loss of 0.01%. Whereas if you go to a 4G connection, this packet loss, average packet loss, goes to 0.5%. Still seems like a very low value, right? So 0.5% of packets lost. However, due to the fact that today we are using HTTP and TCP and all of those stacks, 0.5% of packet loss is sufficient to decrease the speed of the connection by 5 times. Okay, so that happens, as I mentioned before, way more common than in wireless than in the wired part of the equation. So the wireless link is not only presenting higher packet loss, higher latencies, but also higher instability. So for example, on the top, you can see same cells, different carriers experience completely different performance in the same cell, right? Even if you pick the same carrier and look at what happens throughout different days of the week, you can see that for the same carrier, different day means different performance for the same cell. So this means basically that for an end user, you build a spectacular application. Today is having a very good experience on his 4G connection, let's say at his favorite coffee shop. But tomorrow, same place, same device, same user, the experience can be completely ruined. And that's enough for the user to get a bad perception about your mobile application. So a little bit more on the instability side of wireless. Like as you can see, these are latency numbers mainly from the US. And you can see that the variability is very, very high. And then on the right, you can see that signal strength. So in other words, how far away you are from the antenna has a tremendous impact in packet loss. And so as a consequence, if it has a tremendous impact in packet loss, as I mentioned before, it will mean your connection will decrease the speed significantly. And so, like trying to wrap it up in a picture, sorry. So everything that the industry is doing today is you optimize a lot the mobile application by compressing the content as much as you can, by reducing the number of calls, by optimizing your app. Most notoriously, what you do is, or what the industry does, is to use CDNs to basically place the content closer to the end users and therefore increase the speed because you decrease the latency. And that's all helpful. However, when you look at what happens when you're trying to deliver content to a mobile application, you can see that 90% of the link instability actually happens over the wireless link. So let that number sink in. 90% of the link instability happens over the air. And this basically means that today, mobile applications have no control of this phenomenon, right? Because you design the app, you optimize everything you have in the cloud, but then you're left at the ends of whatever the 3G, 4G, or Wi-Fi link of the end user is capable of delivering. And the root cause, and this is something that I will show you next or try to convey you next, and the root cause for this is the fact that today we are relying on solutions that are based on protocols called HTTP that uses TCP underneath. And this basically, TCP was a protocol designed way more than 30 years ago that was designed having in mind wire communication. But today, the reality is that communication is wireless, and for mobile applications, it is definitely wireless. So it's not suited for that use case. That's what I'm trying to convey. And so, in other words, we need to come up with solutions that are capable of providing an end-to-end control in terms of content delivery to mobile applications to avoid being left at the ends of what happens in the wireless last mile. And the last part of my talk is I believe that the solution for this problem lies in using new transport protocols to overcome what the wireless is presenting to us. So let's start first to look at why current solutions are not suited for wireless communication. So TCP, the standard protocol everyone uses today, uses packet loss as a signal of network congestion. So what does that mean? Like when TCP detects a loss, it will immediately decrease the speed of the connection because he assumes that too many people are trying to access the same pipe, and so you should decrease the speed so that everyone can have a fair access to that medium. However, when we are talking about the wireless link, the reason for losses go way beyond congestion, right? You have interference, you have moving around, getting further away from the cell tower, someone opening up the microwave, you're turning your phone around, like tons of things that can happen that create packet losses that are not due to congestion, right? And so for TCP, these losses are due to congestion, and so it will decrease the speed. However, it would not be necessary to decrease the speed, because these are not losses due to congestion. These are losses due to interference. So the next part of why TCP is not suited for wireless communication is, how do you recover from packet loss? So basically, and this is like a very high level example, the way TCP handles communication is, you send a packet, then the receiver acknowledges the reception of that packet, then you send the next packet, and so on and so forth, until a point where a packet is lost. And when that packet is lost, what does TCP do? It retransmits the lost packet. And why is this highly inefficient? Because if you think about this process, this is highly dependent on the time it takes for a packet to travel from the sender to the receiver, and then from an acknowledgement to get from the receiver back to the sender. So in other words, overcoming losses via retransmissions are highly affected by latency. And as I just mentioned before, over a wireless link, latency is higher. It's not only higher, it's actually way much more unstable than when compared to a wired link. And so if we go a little bit deeper into the details of how TCP works, recall that there is no God in this communication, so either the receiver or the sender has to detect that there is a loss. So that is usually done via timeouts, right? So either the receiver sends a packet, waits for a while, the sender sends a packet, waits for a while, the receiver says nothing, and then the sender assumes, well, that packet must have been lost, resend that packet again. So this time, again, is highly affected by latency, because typically TCP computes this timeout as a function of the network latency. And then this can lead to other phenomena. So similar behavior can happen on the receiver side, by the way, but this can lead to other phenomena, which is due to the fact that wireless is so unstable. What can happen is, you send a packet, the sender sends a packet, the receiver gets this packet, sends the acknowledgement, but the timeout on the sender side was shorter than the time that this this acknowledgement took to get to the sender. So I'm talking about this example right here. So in this case, what happens is the sender thinks that the receiver has lost packet 1, and so retransmits packet 1, but actually the receiver has received packet 1, and the acknowledgement is coming later on. And so what happens is, you'll get first duplicate AX, which for TCP is like the end of the world. Speed goes down dramatically because TCP handles very poorly with out of order packets. And so again, all of this is highly dependent on latency, highly dependent on the variation of latency, so jitter, which in wireless links are way much more dramatic than what you have in a wired communication. And so recently, an initiative started by Google started to bring in this new transport protocol to overcome the challenges presented by existing communication protocols. And so it started with Google, then Facebook, Uber, Cloudflare, Fastly, a bunch of others joined the quest. It started as Quick, today is being referred to as HTTP 3. And so basically Quick is a new, Quick HTTP 3, sorry, I will be confusing those two for a while. But basically Quick is a new transport protocol that basically replaces the bundle of TLS, so the security component, and TCP, the transport component. And so basically in Quick does those two functions. One interesting aspect of Quick was that it was deployed on top of UDP. Why? Because otherwise, if you don't deploy it over UDP, that means that you need to change TCP. And to change TCP, you need to change the kernel of every device you have in the network. So that's not feasible, right? So that's why you choose, or the community has chosen to go to deploy Quick over UDP, because you can still do whatever you want to do in terms of transport at the application layer, and use UDP underneath without changing anything on the operating system. All right, too much about that. So what does Quick bring to the table? Basically, by combining session and encryption in the same protocol, Quick is able to significantly reduce the number of handshakes you need to establish a connection to a server. So by default, Quick enables a 1 RTT connection in contrast with the 3 RTT connection that HTTP 2.1 require. But most interesting is that if you're talking to a server that you already know, Quick is actually capable of establishing this connection with 0 RTT. So first transmission is already data because you already have the keys for that server. So what does Quick bring in terms of performance? So far throughout the literature, we can see that Quick is capable of delivering a good performance under high latency scenarios and low bandwidth conditions. And that, Quick performance impact is particularly relevant for small requests. So for example, some numbers from Uber for the P95 and P99, you can see that the improvement, the significant improvement that Quick brings to Uber's application. Here, a little bit more detail. Quick has multiple different implementations out there, and so as you can see here, like for example, when you start increasing, if you look here, when you start increasing the request size, the benefit of Quick actually disappears or becomes negative, for example. And then in particular, if you have some extra delay and again increase the size, the same behavior happens. You start to lose with respect to TCP. But having that said, like Quick's impact can be quite significant for small requests, as you can see right here. So comparing Quick to TCP, what are the differences? So difference number one, the way you establish a connection, right? In here, Quick brings a tremendous improvement. You can go, it goes from 4 round-trip time connection establishment to 1 RTT or 0 RTT connection establishment. So that's a tremendous improvement on Quick, brought by Quick, sorry. According to the literature, it's also said that Quick brings an improved congestion control, right? So, in my opinion, that's so-so, right? Quick does open the door for you to play around with congestion control in the sense that you can just change it at the application level and try it out. So it makes it much easier to develop new congestion control algorithms. However, when we look at what's out there in terms of production, the rate control, congestion control mechanisms being used are very similar to what TCP is using. This is always changing, but from what I saw last time, the tendency was to go towards New Reno. Quick also brings an improvement with respect to the problem of head-of-line blocking. It does not solve it entirely, but it does help a lot with respect to this problem. And finally, a very interesting feature, connection migration. So what is this? Like you're watching some video in your office, connected to your office Wi-Fi, and then you go out of the room, you lose your Wi-Fi connection and you go back to cellular, right? Today what happens is when you go to cellular, your phone needs to establish a new connection. So to drop the former connection and establish a new connection, right? And if this is with a standard HTTP, this means again, new 4 RTT connection establishment to the server. With Quick provides an abstraction to the tech that you are using to connect to the network, and so is able of offloading from Wi-Fi to cellular or vice versa without needing to renegotiate the session. So you just continue to communicate to the same server without any new keys being agreed, which for this edge case of Endover is quite a significant improvement. However, and this is my personal view on it, so is Quick the silver bullet? Is Quick the thing that will help overcoming the problems that wireless communication poses to mobile apps? I don't think so. So it is true that Quick optimizes a lot the handshake. However, if I didn't talk about the rest, because the rest of the transport, so the way you recover from losses and the way you do rate control is exactly the same as TCP. And so this is why when you say, okay, Quick has a big impact for small requests, makes sense, right? Because if the request is small, the handshake is a large portion of, so the handshake is a large portion of that, right? However, if the request is big, the handshake is a very small part of that. And so the impact of improving the handshake becomes marginal, and therefore the impact of Quick will be marginal. And so if we recall the two major problems of TCP that I've mentioned before for wireless communication, number one, loss recovery is based on retransmissions, right? So it's highly inefficient, as I mentioned, in the presence of latency. And assuming that all losses are due to congestion, and which leads to decreasing the speed, these were the two main flaws of TCP when looking at wireless communication. Quick behaves exactly the same way as TCP with respect to these 2 points. Sorry. Quick still is an ARQ-based protocol, and he still assumes that that the loss is due to congestion, and therefore the problem is still there. So now I'm going to introduce you to a new technology, which is called network coding. And the question is, can it help? So what is network coding? So network coding can be a wide variety of things, but it basically means operating over data packets. So for example, let's say you have 3 packets to send. Traditionally, the way you transmit these packets to a receiver is you send packet 1, then you send packet 2, then you send packet 3. With network coding, what you do is you combine these original packets by, for example, doing an XOR of 2 of those packets and transmit the result of that operation. So in this case, for example, what you transmit is the result of P1 plus P2, the result of P2 plus P3, and the result of P1 plus P3 to the receiver. So then the receiver gets P1 plus P2, P2 plus P3, P1 plus P3, which is basically a linear system of equations to solve, right? And so going back to simple algebra, you can take that matrix, invert that matrix, and the receiver with this is capable of getting the original P1, P2, and P3 exactly what the sender wanted to deliver. Right? So the question, why should we care about this, right? What is it used for? So let's take this example, right? So the sender is transmitting to the receiver, and there is a loss in between, right? And so in the end of this process, the receiver gets P1 plus P2, P3 plus P4, P2 plus P4, and P1 plus P3 plus P4, right? And so I will spare you the details, but with these 4 transmissions, the receiver is capable of recovering the original 4 P1 to P4 packets, right? And all of this can be generalized, actually. So in general, with network coding, we are able to deliver n successful packets to a receiver with just n successful transmissions. And now comes the important part. Irrespective of what transmissions were lost. So in other words, as long as n packets get to the receiver, no matter what those n are, the receiver will be able to recover all the original information. And so this basically means that you can achieve this with network coding without needing to know which packet was lost, and as a consequence, without needing to wait for feedback to overcome the loss, right? So when you compare network coding to standard protocols like TCP or QUIC, whereas in ARQ, in TCP or QUIC, as I mentioned before, you do ARQ. So to recover from a loss, you have to do a retransmission, and you are highly dependent on latency. If you are using a network coding based protocol, you do not need feedback, and so you are not subject to latency to recover from losses. So latency has no impact in how fast you recover from a packet loss. And then on the other side is, as I mentioned before, TCP and QUIC, whenever a loss occurs, they typically assume it's due to congestion and they decrease the speed, right? With network coding, and I will spare you the details because it involves complex linear algebra, but by looking at the matrix that the receiver and the sender have, with network coding, when a loss occurs, you are able to distinguish a loss that is due to congestion, in which case you behave just like TCP and QUIC, decrease the speed so that everyone can get the fair access to the channel. You can distinguish those losses from the losses that are due to wireless things, like interference, movement, whatever. And if the loss is due to wireless phenomena, you do not need to decrease the speed of the connection. Why? Because those losses will already be overcome by the network coding that you are using to transmit the packets. So just to give you a little bit of comparison in terms of results. So here we have the one to the left, Balena, is a network coding based protocol. Bustazayo, the second one, is an HTTP2 connection, and the other 3 are basically 3 different implementations of QUIC. And here we are comparing all of these setups for small requests for 2 different packet loss rates. And as you can see, for small requests in the beginning, so for small latency, everything is very similar, right? So all the protocols are very similar. But as soon as you start to put some latency on a link, what do you see? Number 1, HTTP going down quite dramatically. Number 2, you see that all protocols lose some speed, which is natural. However, the network coding based protocol, Balena, is way much more resilient to the increment of latency. And the same thing happens on the right side, where packet loss is higher, so this phenomenon is more clear. And when we go to larger requests, so in this case I exaggerated a bit, so I have to apologize, it was the data that was more at end at this moment. So I'm looking at a request of 17 megabytes. And here I think the picture talks by itself, like the impact of using network coding is brutal in terms of what you get in terms of throughput, right? So it becomes very clear that network coding based solutions can be the future of content delivery for mobile applications. Thank you so much.